So today we're going to start with one example, and we're going to take a look back at the particle in motion along the x-axis. So we're given ds dt, which is our velocity function, and it's given by t squared minus 8 over t plus 1 quantity squared. This is for time 0 to 5. So this is the velocity of a particle between 0 and 5 seconds. Here's a graph of our velocity function. So the first thing that I notice as I look at this velocity function, it starts off negative. So at t equals 0, I have a negative velocity, which means the particle is going to the left. It starts off going to the left. Then at a little bit after 1 second, the particle stops, turns around, and starts heading back towards the right. So now we're going to start to look at, given the velocity function, can I tell where the particle is? Well, suppose the initial position of the particle is given by s of 0 equals 9. What is the particle's position at A, 1 second, and B, 5 seconds? So we know that if it starts off at 9, and after 1 second, it's going to be going to the left. So when we find its position probably should be something less than 9. Okay? We know that velocity is the derivative of position, so it would be natural to think that position is the integral of velocity. So what we're going to do to find its displacement, okay? The integral is going to give me the displacement of this particle, meaning it's going to give me how far it's moved, okay, between a certain time. So if I look at the integral, so for part A, if I look at the integral of my velocity function between 0 and 1, it's going to give me t squared minus 8 over t plus 1 quantity squared dt. If I look at that integral between 0 and 1, that's going to give me the displacement of my particle, meaning where has it gone in relative position to where it started. So if we integrate this function, we can say this is t cubed over 3 minus 8 times, actually let's do it this way. Let's go the integral of t squared minus 8 times t plus 1 raised to the second power. If I think of I can use substitution here. It's all dt between 0 and 1. I can think of using my u substitution. Okay, so we're going to end up with t cubed over 3 minus 8 times t plus 1 raised to the negative first power divided by negative 1, bounded between 0 and 1. So if I plug in my values, I'm going to get, well, we can rewrite this as t cubed over 3 plus 8 over t plus 1, bounded between 0 and 1. That's going to be 1/3 plus 4 minus 0 plus 8. So I'm going to get, that's 12/3, so we have 13/3 minus 24/3, which is going to be negative 11/3. So that means after 1 second, this particle has gone left 8 negative 11/3 units. But the question was, where is it after 1 second? If it started at 9 and has gone to the left 11/3 units, okay, to find its new position is going to be equal to its starting position plus the displacement. So in this case, its new position is going to be, it started at 9, and then we're going to add negative 11/3, and so I'm going to get 27/3 minus 11, which is going to be 16/3. So its position after 1 second is going to be equal to 5.33, or 5 1/3. Okay? So again, you can see that, again, what the particles are doing, if we're talking about the position, so this is the velocity, if we're talking about the position, okay, or even if we're just looking at the motion of the particle, it starts way out here at 9, but during this first second, it's going to move. We already talked about it, should be to the left of 9, so it moves to the left, and at 1 second it hasn't turned around yet. Okay? But what's going to happen is if we look at it at 5 seconds, it's going to come out here, and we know at 1 second it's going to be over here at 5 1/3. It's probably going to go a little bit further, and then it's going to turn around, and it's going to go back this way. And it's probably going to end up someplace to the right of 9. So if we want to find its position after 5 seconds, we're going to take this same little formula here, and we're going to go ahead and do it for 5 seconds. We've already found the derivative now, or excuse me, the integral. We've already found the integral between 0 and 1. So for part B, I'm going to take and integrate to find its displacement between 0 and 5 of t squared minus 8 over t plus 1 quantity squared dt. Okay, again, this integral is just my displacement. Okay, this integral right here is just the displacement. And we've had a lot of conversations about what displacement is, but it's not total distance traveled. It's where you are relative to where you started. Okay? So again, if I start way over here and I walk 5 paces and then I turn around and walk back 5 paces, my displacement is 0 because I haven't moved from where I started. So this integral again is going to give me the displacement of that particle from where it started. That's why its new position is your starting position plus your displacement. So if we go ahead and integrate this, we've already actually done a lot of the work here, but if I integrate it, I'm going to get the integral from 0 to 5 of t squared minus 8 t plus 1 quantity squared dt. That's going to be equal to, and I'm going to jump right down here to this spot, because when I integrate it, I'm going to get t cubed over 3 plus 8 over t plus 1, bounded between 0 and 5. Go ahead and plug my bounds in. 5 to the third is 125 over 3 plus, that's going to be 6/8 plus, or 8/6, which that reduces down into 4/3. Oh, good. Life is pretty easy there. Minus And it's going to be minus 8 again, because when I put in 0, I'm going to get 0 plus 8. So then we go ahead and take 129 thirds minus 24 thirds, which is going to be 105 thirds. I've done everything correctly. And it looks like that is equal to 3 goes into 10 3 times, so that should be 35. So now my new position, again, if I come back over here and I think of position, I've gone back probably a little bit past 5 maybe, and then I've gone off this way. And again, the velocity is increasing, so it makes kind of some sense that the new position is that much further beyond 9, because the velocity is increasing. That means it's going faster as it goes that way. Okay? If we're just thinking of the pure velocity graph. So after 5 seconds, it's at a position of 35 units. And after 1 second, it's at 5 1/3 or 16 thirds. Questions on any of that? Sorry, I can't answer them if you have.